In this section, we're going to go over how NRLMOL handles its files. That means what files are required to run an execution, what files are created, and what files are required to restart a calculation. First of all, you need the binary program, the executable program. Okay, so this can be called NRLMOL _exe cluster or cluster.opt. You need the capital cluster file. This has to be in capitals, and this file contains the molecular structure which will be calculated, and the file NRLMOL _input.dat in case some post-convergence requirements are needed or other tweakings to the program are being needed. The JavaScript file, in case using of a remote cluster, you have to check, however, what format they use over there. So here's a typical cluster file, in this case methane, which I'll be executing here in a moment. The first line defines the exchange and correlation for the calculation. So first, for the exchange, we can have either GGA or LDA. Okay, the definitions are shown on screen, so this has to be there. Then you put a dash, then you put the functional which you're going to use. In this case, I'm using Purdue, Berg, Erzenhoff, or other options are specified here. Then you put star or asterisk. Then you define the correlation, and same options here. Okay, GGA and LDA, same for the function. Next up, we have the point group. Okay, in this case, I'm using GRP, which is when you specify explicitly the positions of the atoms. So you're using creating a structure by symmetry, then you use some of the other options listed here. Okay, and just list the equivalent atoms. So next up, in this case, 5, the number of equivalent atoms for methane. So then you describe all the atoms. The first 3 columns, of course, the X, Y, and Z positions in atomic units. Okay, the equivalence between atoms is shown on screen. Next up is the atomic number, in this case 6 for carbon. And lastly, all or BHS, all when using the effective potential. We say that you're using a null-electron calculation, or BHS when using a pseudopotential. Okay. After you describe all the atoms, then there's two extra numbers that must be specified, which is the net charge of the system. In this case, for neutral charge, here we have 0, and the net moment of the system, meaning a closed shell system. Okay. The NRLMOL input.dat, as I said, this file is not required if not requesting any special calculations. Okay, it will be created, however, by default if not present in the directory. And if you initially do require, there is a copy of it in the source code. Okay, executing the program now. You execute the serial version by just doing that /NRLMOL >print.log. Okay, so let me do that in my terminal here. As you can see, I have a calculation set up, which is just the capital cluster file and the binary file. Let me just show you the capital cluster file. And as I said, it's methane. Okay, so I have GRP, and I have 5 number of equivalent atoms. In this case, the program just reads the number 5 and disregards everything else. Same for the last line. You have the 0 for the net charge, 0 for the net moment of the system, and the text afterward will just be ignored. So let me just do that /NRLMOL >print.log. I'm doing that because that actually saves all the output in that the program generates into that file, print.log. So let's go back to the presentation. Okay, and as I said, we use this >print.log to redirect the output into this file, print.log. It can be called whatever you want. Print.scf. Sometimes I use log.txt. So whatever you want. This file would just contain the output of the program itself. Now, when you are executing the parallel version of NRLMOL, you have to specify MPI run or MPI exec or whatever command to execute MPI programs on a remote cluster is. You specify the number of processors, /NRLMOL, and you do the same. You redirect the output to some text file. Okay. When you're executing a remote cluster, you have to check the job scheduler format. That means on the remote different clusters, they may have different ways to do a job request to the server over there. Okay, so what happens when we execute NRLMOL? Well, from the cluster file, some information will be taken and other files will be generated, written out in the directory where you're executing. Okay, First of all, the parsef file. This contains a copy of the params file from the source code. If you already saw the other tutorial on compiling NRLMOL, you know that this file resides in the source code and specifies some of the sizes of the arrays that NRLMOL uses. Okay, so a copy of it will be stored here in this calculation, in the directory where you're running a calculation. The symbol file is generated, which contains mainly the atom positions, that is the geometry. Okay, whenever you restart a calculation and the symbol file is present, it takes precedence over the cluster file. Okay, the ISIMGen file, okay, which contains the basis set information, RepMat, the representation matrix, GRPMat, the point group rotation matrix, runs, which contains the restart information, geoconverge, shows if the calculation has converged or not at the end, and xmol.dat and xmol.xyz, which is the structure in XYZ format. The difference between those two files being that xmol.dat contains the atom definitions in numbers and xmol.xyz contains the atom definitions in letters. Okay, and there's another file called PSP when you're using pseudopotentials. Okay, so during the calculation, the code will require several iterations in order to converge, in order to achieve a self-consistent field. Okay, a file called eval XXX will be generated for each iteration, where XXX will take a number, in this case being 001, 002, depending on how many iterations the program needs to finally converge. And also, a summary file will be created initially and then updated with the energy for every iteration. Okay. There's also a geoconverge file, which sets the convergence criteria. There's a flag there which will be set to true or false depending on the output of the optimization. It also contains the final energy, the total gradient, and the largest nuclear gradient. Okay, so let's go back to the terminal and check the calculation I set up, and you can see I have my prompt back. That means it finished. If I do ls, I see a number of files that have been created there. Some of them I already discussed, like the eval files. You can see geoconverge, grpmat, and as you can see, nrlmol-input.dat has been created by default there, and some of it's, of course, it just sets some default options there on the file itself. Okay, so let's do more for geoconverge. And you can see that the converge is false. That means that this structure hasn't converged yet. The energy is minus 40.467078. Okay, and you have the total gradient and the largest nuclear gradient. You can also open the print.log file that I created, which contains all the output from the program. Okay, and you can see, you can even go to each iteration and see what the outcome was and what the energy was for that specific iteration. Okay, so let's go back to the presentation, and as I said, the summary file will contain for every iteration the traces of Hamiltonian, the total energy, the kinetic energy and non-local contributions, and the total charge. So let me just print down on screen here the summary file. Oops, summary. Okay, and you can see iteration 1 to 8. The trace of the Hamiltonian and the energies, you see how it's changing. The last three iterations, of course, are practically the same because the convergence criteria is set to 1 to the minus 6, which actually doesn't show on screen. Okay, so let's go back to the presentation. The values file contains the number of bases, the Fermi level for this structure, the occupations and energies for the electrons. Symbol file, which contains an updated geometry. Okay, that means that whenever you're running a calculation on NRLMOL, at the end of the SEF cycle, it usually predicts a new geometry, which will be the input for the next step when you're doing an optimization. If you're just doing what we call a single point run, then you don't need to worry about this new geometry, and you can even delete it. Okay, so FRC out contains the force on each atom and the maximum force on, that means what atom contains the maximum force on it. At the end, of course, these forces are calculated. So whenever you're restarting a calculation, as I said, you don't necessarily do it from the cluster file. Okay, so you actually need the symbol file, which contains the geometry. You need ISIMGen, which contains the basis set information. You need grpmat, RepMat, okay, the group rotation matrix, the representation matrix. Okay, that will no longer require the cluster file to be present in the directory. Okay, you need runs, which contains the restart information. And in it, you can specify starting from a given evaluation. With it, you can use the existing mesh, which is written in VMOL. You can start from the Hamiltonian, from the potential, or from the wave functions, from these files that are being described here. Okay. GeoConverge file, in this case, it's recommended that you actually remove it from the directory, just in case the structure is already converged. Okay. So the runs file, for the first line, the first column contains the information from either what evaluation you want to start, or if you want to use the existing mesh that was created during the calculation. The mesh calculation can take some time for large systems, so you just put a -1 there to use the existing mesh, which is stored in the file called VMOL. If you want to start from a given iteration, in this case, if you want to start from the 4th iteration, you put a 4 there, and you make sure that the file eval004 is present in the directory. Okay. Next up on the second column on the first line is from what geometry you want to start the calculation. In the symbol file, as I said, there's first of all a calculation that is created by the program from the information from the cluster file. Let me just open the symbol file so you can see this. So as you can see here, it says one calculation set up by iSetup. That means that this subroutine iSetup in NRLMOL just took the geometry from the cluster file and put it here. You can see it's the carbon in the origin and the coordinates for the other 4 hydrogen atoms. But then it says new calculation created by update. That means that after the code converged in the SEF cycle, then new coordinates for the hydrogens were calculated or predicted by the program, and they're now being set up here. So when you restart the program is asking you in this second column on the first line in runs which geometry you want to use, the first one or the second one. In this case, going back to the presentation, we put 1, so we start from the first calculation, so from the first geometry. Okay, that means the other one we can actually take it off. If you want to start from the second geometry, put a 2 there. Okay, second line, the first column is where you want to start the calculation from the Hamiltonian, from the potential, or from the wave functions. In this case, you put a 1 there, and the files HAML, which is the Hamiltonian, and OVL baby, which is the overlap. The Hamiltonian overlap matrices are stored. They have to be present in the directory. If you want to start from the potential, you have to have the file patall present. If you want to do a least square fit, you just no extra files are required to be in the directory. But if you want to start from the wave functions, you put a 4 there, and you make sure that the file wfout is present in the directory. And that's how you restart calculations from NRLMOL, which they don't necessarily always have to be from the cluster file.